So in this example number 2, we're going to understand how we analyze the thread strength for a power screw. Um, so we're going to go back to the same example we discussed in example number 1 in the previous example. It's a continuation of that example. And what we're going to do in this particular problem is we're just going to add some information for this was moving cyclically. So the problem says that you have grade 4 and 8. We can assume that this is SAE certified. And we want to know if this is going to be safe in static and fatigue. So in static, we're going to be concerned mainly in the rising, when you start in rising. And in fatigue, we will worry about when it goes up and down, up and down, up and down. Okay, so let me write this down here. So for static, your main focus is when you start, this is the more critical part in rise. Okay, and then in fatigue, then as you know, we are actually just going up and down, up and down. We are F maximum and F minimum. Okay, then this is given in the problem. These are material properties that are given for this particular material. So this is your yield, tensile yield strength. This is tensile ultimate strength. And this is a fully modified endurance limit, so it has all your K infinite involved here. So this is the final, this is the value that you will use for analysis. Now, this is very typical. Many times we get information in terms of marginal safety. In this case, this margin is 0.50, says 50%. So this is basically saying that you have a design factor that is your marginal safety plus 1. So that means that your design factor will be 1.5. So that's basically embedded in your analysis. So the first thing you do in the problem is you want to, so we're going to do a static analysis. Okay, that's the very first thing we do. Static is the static check. I cannot emphasize enough, don't do fatigue until you make sure you're safe in static. Okay, the fact that it's safe in fatigue doesn't mean it will be safe for a static load, and you want to make sure that both are correct. If we just use the information that we had from your previous example, we found that this was equal to this. We found that your F max, again, this information comes from example number 1, and F minimum was 2000. Okay, this is pounds, and this is inch pounds. So from here, I can find what my T is. The T I'm going to use for my analysis is your design factor multiplied by TR, and that will give you a value of 1,167.7 inch pound. And the force I'm going to use for static analysis is the maximum load. Okay, and multiply by your design factor, so that would be 3,750 pounds. And just remember that your design factor is 1.1. And the other thing I also need is all the geometry information. So your pitch is 0.25 inches. Your mean diameter or your pitch diameter is equal to 1.25 inches. And then your root diameter is 1.125 inches. And your major diameter is 1.375. And we got all this information from your example number 1. You may want to look the example 2 as a refresher. Okay, so once we have this, then we're going to do 2 checks. Now, we don't need to check point B, but I want to just show you that this point is not going to be critical at all. Okay, so if I was to do this, And you have a MATLAB code that actually calculates all these values. And your F and your T come from here. Is this F and T. Is these F and T's, okay, not TR or F max, is the one that's modified after you multiply your factor of safety, your design factor. So once you replace these values there, and I am just going to give you up to the 3 decimal in your handout. That's actually a full complete set of notes that you can actually follow. Um, I'm just, for the sake of saving a little bit of time, I am going to just give you a couple of decimal points. And this is at this is all in KSI. So the end goal, what you really want to do in this problem is you want to find sigma 1, sigma 2, your principal stresses. And don't forget, this is always the highest. So this is 4, this is 0, this is minus 7.6. And then from here, you find what's your von Mises stress. Von Mises is 9.697. And then from here, this is all in KSI, by the way. So your factor of safety, then will be yield strength divided by sigma von Mises, and that would be 36 is given in the problem. Okay, this is 36 divided by 9.97, and this gives you 3.71. So you can see it's bigger than 1, and it's not going to be a concern. So we go to point number 2, at point C now. That's more interesting for us. And I want to show you that you're actually going to get a lower values for your factor of safety. That's what's going to show you that's more critical. And I already did this math for you. So if you replace all these values that you already have, you know all this information from previous example. So all you have to do is replace the numbers here, and you get this state of stress. From this state of stress, you can show that sigma 1 is equal to, just give me a minute. Okay, so from this state of stress, this is 64. And again, in your notes, you will have a full set of notes here. I am all the decimal points. I'm just saving some time here. This is all in KSI. And from here, then I can find your von Mises. Your von Mises is 12.78. And then from here, you can show that your factor of safety is tensile, yield strength, and sigma von Mises. And that gives you 36 divided by 12.078. And that would give you a value of 2.98. And what you can see is that at point C, as you can see in this problem, that point C is way more critical. Okay, point C, I get this value. At point B, I got a higher value. This is point B. You can see I got 3.71, and this one I got 2.98. So the likelihood this will fail first before point B fails is great. So that's why we just focus our attention to point C. Okay, that's what we want to do in this problem. Okay, so the next thing we want to do is, now we are done with static. Now we're going to move, and we will do fatigue. So this is the fatigue check. Okay, and then fatigue check, what you want to do is you want to your new F max, you want to modify all these, okay, by using your design factor. That's important that you always take care of that. So this is 1.5 times 2500. This gives you 3,750 pounds. This gives you 1.5, 2,000. This gives you 3,000 pounds. And since we are working in a cyclic loading, And so the uh, the coefficient of friction that I'm going to use is at running, and from problem this is at running, and this is from example number 1. Okay, you can go to example number 1, you will see those are the values I used. So you have this information now. The next thing you want to do in the problem is you want to go ahead and find what your alternate F alternate is. F alternate will be F maximum minus F minimum divided by 2. That gives you 375 pounds. So you subtract this minus this and you divide by 2. Then you want to find F minimum, mean, and F max minus F mean divided by plus. Okay, this is, you add this to and divide by 2 and you get this is 3375 pounds. Once you have that information, then your next step is basically come and you calculate what your alternate and mean torques are. And so you just replace the values here. And what I want to highlight here is all this information is given in the problem, right? Even your L is given. Remember, L was 3 times P. That was equal to 0.75 inches. Okay, so we know your L. We have all the information you need. This is your mean diameter that's given, and you just calculated this in the previous slide, right? We have this, and U alpha is 5 degrees. Don't forget that. That was from your previous example. So when you evaluate all this, you get a torque of this value. Okay, so now that I have the torque, the next thing I want to do is I want to find your fatigue stress concentration factor. Okay, the fatigue stress concentration factor, this is what I'm going to do. So I'm going to start with RF. It's going to be 0.06 times the pitch. This is 0.06 times 0.25. That would give me 0.015 inches. Okay, inches. So this is your RF. Your diameter is 1.375, and that's given in the that's actually given in the previous slide. Given in your previous example. That's where this comes from. Okay, so now now that we have these values, then the next thing I'm going to do is I'm going to use the fillet. I'm going to go to Appendix A and for the fillet, but before I do that, I need to use these values. I need to find big D over small d. And according to your notes that I gave you, it's not in your textbook, this would give you 1.375 divided by your root. That would be 1.125. That gives you 1.22. And your R over D then would be RF divided by DR. That gives you 0.015 divided by 1.125, and you get 0.0133. Okay, so now I can go to the charts, and I'm going to find this value, 0.133, and look what happens here. Now this doesn't intersect these curves at all. I don't have these curves. It is incorrect to say, oh, this is going to be more or less, I can keep it, I can keep extrapolating this. No, you cannot do that. You don't have test data. You don't know what the behavior is going to look like, so you are not allowed to do that. You don't have the information, then we have to use another means to do that, to find that data. So I found this as 2.3. For this particular example, I decided we can use then the table 8.16. Table 8.16, the problem said this was grade 4 to 8, and we could assume this is SAE grade. So I'm working with fillet. Remember, this is only for axial load, okay? Only for axial, nothing else. Then I can use this value. So this is the correction factor, will be 2.3. This is already KFA. I don't need to modify, I don't need to do anything else. Okay, so now for your bending, I can go here. This is 0.133, and this value is 1.5. This value is 1.10. So roughly here, I'm going to have 1.22. That's the value of d over small d. So roughly this gives you 2.7. This is good approximation for that. So I'm just going to go ahead with that value. Okay. And for torsion, remember these are static values. These are static. Okay. This is 0.0133. And then this is 1.2. So it's roughly a little bit on top of that. But this is all approximation anyway. I will go with 2.2. Okay. Now, this is static, so I'm going to need my notch sensitivity to make my corrections to get my fatigue stress. Remember, this was 60. That was given in the problem. So if you look here, this is 60. Okay, that's the ultimate tensile. So since that is 60, and this is 0.015, but this is R, and the roughly is there, and this is approximately, this is 0.5. And then here this is 0.0115, again goes to 60, and I found this is just about 0.58. It's a good guess estimate and it's acceptable. Okay,